So good morning, students. Myself is Shankar from EC Department, Chevrolet Engineering College. Today we are going to start a new unit, sampling. It is a third unit as per your syllabus, R-19 for the second year EEE students. It is a very important and easy sampling. So first of all, so what is a operation? The first operation in the digital communication is nothing but it's a sampling. There is two communications we have. That is the one is analog communication and the digital communication. The first operation in the digital communication is a sampling for the discrete time functions here. Also, almost all the natural signals exist in the form of in analog form. For example, voice, any moving screen, environmental data, etc. exist in the analog or continuous form. You know, the digital or the discrete or analog form. Analog form is always in the continuous only. Discrete means it is in the digital means it is in the discrete form or discrete time domain function, continuous time domain function. Yes, such information can be transmitted from one place to another by continuous modulation of the suitable carrier. Means what is it carrier? We have the modulation, a small signal, the voice signal is modulated with the carrier, the high frequency signal. Carrier is nothing but the high frequency signal, and the voice signal is a low frequency signal. Low frequency signal is modulated with the high frequency signal, and it is carries from the transmitter to the receiver. At the receiver side, it is demodulated, means the carrier high frequency signal is separated and only it is received at the receiver side is a low frequency signal. Nothing but the voice signal, whatever it is, we are sending from the transmitter to the receiver side. Okay. So modulation and the demodulation occurs from transmitter to the receiver side when any signal is transmitted. Such information can be transmitted from one place to another by continuous modulation of the suitable carrier. Then this type of communication is called the analog communication. Okay. And in the digital communication, the data is to be transmitted is sampled at regular intervals. The digital communication means, first of all, you can take the analog communication, analog signal. So this is the analog signal we have. Let us assume the x of t signal like this. Okay, from minus infinite to infinite, and it is sampled by using the impulse functions. So let us we have the impulse functions like this. From minus ts, minus 2ts, and another one here, the ts, and the 2ts, and so on. All around is the delta ts of t. The x of t signal is sampled with all the delta of signals, the sum of the functions, sum of all the functions of the impulse function. It's a regular intervals, sampled at the regular intervals. Such samples are transmitted directly or through the modulation of some carrier. There are various sampling techniques here. The sampling techniques affected the spectral content of the signal. So there is a different types of sampling techniques. after the sampling the continuous time signal, we have to transmit directly or through a modulation of some carrier signal. Nothing but is a digital communication. The analog communication, we are sending the analog signal, and in the digital communication, the analog signal is sampled at a regular intervals. Such samples are then transmitted directly. Okay. So what is the sampling theorem? So what is the sampling theorem? Sampling of the signal is fundamental operation in digital communication. The first operation here, sampling of the signals is a fundamental operation in the digital communication. A continuous time signal is first converted. What I told here, a continuous time signal is first converted to discrete time signal by sampling process. See, we have the block diagram. First, you can take an analog signal. The analog signal is the input signal here. It's given to the sampler. Analog signal means is a continuous time signal. Continuous time signal, both time and amplitude, both time and amplitude is a continuous. Okay. Now, after the sampler, the signal is a discrete time signal. Discrete time signal. Nothing but the signal is like this. The sampler at regular intervals. Okay. It is a discrete time signal. Discrete time signal. Here, time is discrete and amplitude is continuous. Amplitude is continuous. Okay, my dear students. After the sampler, sampled at a regular intervals of the given analog signal by using the sampler, you get the discrete time signal. That discrete time signal, the time is discrete and amplitude is continuous. And here, continuous means the time is continuous and the amplitude is also continuous signal. After that, the signal, whatever we got, it is the discrete time signal, is given to the quantizer. The output of the signal is a digital signal. Digital signal. Nothing but both the amplitude and x of t, both the amplitude and the time is discrete. It's a digital signal. A digital signal. Both time and amplitude, both are the discrete. It's called as a digital signal. And after that digital signal is given to the encoder. Here the output signal will get, it is also the digital signal only, in terms of ones and the zeros. Okay. This is a block diagram of the sampler or sampling. What it matters. Given the analog signal, nothing but is a continuous time signal of the x of t. The time is continuous and the amplitude is also continuous. And this signal is sampled at regular intervals of, you'll get the discrete time signal. Here the discrete time signal is nothing but the time is discrete and amplitude is a continuous. This discrete time signal is given to the quantizer. The output of the quantizer is a digital signal, means both the time and amplitude. The amplitude is nothing but the y-axis and the time is in the x-axis. Both these are discrete. In the signal here, when I am saying discrete, is not the x of t, my dear students. Is x of n. N is a variable, and here also the n is a variable. N is a variable. The t only representing of continuous, and n variable is representing of discrete, or it is a digital signal. Okay, the block diagram of sampling. The sampling is a signal, is a fundamental operation in the digital communication. A continuous time signal. A continuous time signal is first converted to the digital time signal by sampling process. The sufficient number of samples of the signal should be taken so that the original signal is represented in its samples completely. The continuous time signal you can take and sample with the regular intervals of time, and you can take the sufficient number of samples here. Sufficient number of samples of the signal should be taken so that the original signal is represented in its samples completely. Also, it should be possible to recover or reconstruct the signal completely from its samples. Construction and the reconstruction. Okay. The number of samples taken depend upon the maximum signal frequency, nothing but FM. It's a hertz is the maximum signal frequency present. Okay. The sampling theorem gives the complete idea about the sampling of the signal. Different types of samples are taken. That is a one time. First one is a flat type samples, regular samples, instantaneous samples, etc. Okay. The sampling theorem, and then it will be see the different types of the sampling process. See the definition of the sampling here. They are saying the sufficient number of samples of the digital of the signal should be taken so that the original signal is represented in its samples completely. Also, it should be possible to recover or reconstruct the signal completely from its samples. Okay. The other way, the first part of representation of the signal in the samples and the minimum sampling rate required to represent the continuous time signal in its samples. Okay. The construction and the reconstruction. So, what is a sampling? Sampling theorem states that the signal which is band limited, the signal which is band limited to FM hertz to the maximum frequency FM hertz. The signal which is band limited to FM hertz can be completely recovered. Can be completely recovered from its samples, recovered from its samples if the samples are taken, can be completely recovered from its samples if the samples are taken, if the samples are taken at a rate of FS sampling frequency is greater than or equal to 2 FM, 2 into the maximum frequency. So this is a sampling theorem statement. The signal which is band limited to FM hertz can be completely recovered, from its samples if the samples are taken at a rate of Fs is greater than or equal to 2 FM. The sampling frequency Fs either it is greater than the 2 FM or Fs is equal to 2 FM. It recovers the original signal by using these two conditions. The sample are taken at a rate of the Fs is greater than or the equal. If Fs is less than the 2 FM, it is not recovered the original signal. This is nothing but aliasing effect. Aliasing effect. So which is nothing but the low frequency signal is getting in the high frequency, and high frequency shown in the appears in the low frequency. Low frequencies appears in the high frequency, and high frequency signal is appears in the low frequency signal. So here it is a whenever if you can take the Fs, the sampling frequency is less than the 2 FM, we'll calling it as a aliasing effect. So three cases: Fs is greater than, and the Fs is equal to 2 FM, and the Fs is less than the 2 FM. This is a sampling theorem statement, my dear. Once again, I am saying here the signal which is band limited to FM hertz can be completely recovered from its samples if the samples are taken at a rate of Fs is greater than or equal to FM. Put it, my dear students. See the band limited signal, the sampling theorem for a low pass signals only. Why we are using to recover the signal by using the ideal low pass filter or by using the practical low pass filter. When we can use the practical low pass filter to recover the original signal, and when we can use the ideal low pass filter to recover the original signal, we can explain in the later. A band limited signal of finite energy which has no frequency components higher than the omega hertz is completely described by specifying the values of the signal at instants of time separated by the 1/2 omega seconds. And the second point saying that the band limited signal of finite energy which has no frequency components higher than the omega hertz may be completely recovered from the knowledge of samples taken at a rate of 2 omega samples per second. 2 omega samples per second. See the 2 omega, you can call it as a time interval, and 1/2 omega is a rate. The above statement of a sampling theorem state that two parts can be combined. The two parts can be combined. The first part represents, the first part here that represents the representation of signals in its samples and minimum sampling rate required to represent a continuous time signals into the samples. The second part of the theorem represents a reconstruction of the original signal from its samples. Okay, the first part is represent the signal in its samples and the minimum sampling rate. The 1/2 omega is a sampling rate and the 2 omega is a interval. And the second part of the theorem represent the reconstruction of the original signal from its samples. Okay, it gives a sampling rate. It gives a sampling rate required for satisfying the reconstruction of the signal from its samples. The theorem can be combined and alternately stated as follows. A continuous time signal can be completely represented in its samples. A continuous time signal can be completely represented in its samples and recovered back if the sampling frequency Fs is greater than or equal to 2 Fm. Actually, it is Fm. It representing as a omega. Here, Fs is a sampling frequency and omega is the maximum frequency. I told it is a Fs is greater than or equal to 2 Fm minus. The same statement I said that it is the signal which is band limited to the FM heads. The signal which is band limited to FM heads can be recovered, completely recovered from its samples. If the samples are taken at a rate of Fs is greater than or equal to 2 Fm. Here it is omega is nothing but the omega Fm. Maximum frequency present in the signal. Got it, my dear students? So both the statements is the same. A continuous time signal can be completely represented in its samples. Completely represented samples is the first part, my dear students. And recovered back if the sampling frequency Fs is greater than or equal to 2 omega. That is the second part. What they are saying in the previous stage. The two statements, and this statement is sampled and this is a recovered. A continuous time signal is completely represented in its samples and recovered back if the sampling frequency Fs is greater than or equal to 2 omega. Omega is nothing but take as a Fm, the maximum frequency in terms of the hertz. Okay, my dear students. Let you take the proof for sampling theorem. Let the x of t be the continuous time signal as shown in the figure. It's a continuous time signal, my dear students. Let this signal be the finite energy and infinite duration from minus infinite to the infinite. And suppose that x of t is strictly band limited. The statement saying that the signal which is band limited, the signal is which is band limited to FM heads. Here they are saying it is a omega, the W. X of t is strictly band limited, that is x of t does not contain any frequency components higher than the omega heads. Higher than the omega heads, band limited. Within that only we have, there is no any higher than the omega heads. A sampling function samples the signal regularly at a rate of Fs, sampling frequency per second. So, you see, first of all, I am assuming a continuous time signal x of t like this. A signal which is band limited to FM heads. Okay, my dear students. Then you take this signal is given to the sampler, and that sampler can sample the analog signal, convert into the discrete time signal. So first of all, I am taking as one function delta of t. At 0, its magnitude is a 1. It is from minus infinite to infinite. Here also you have taken the minus infinite to infinite. Okay, my dear students. This is a given signal is x of t is a continuous time signal. X of t varies with respect to the t here, and here also varies with respect to the t. Second signal, if I am taking here, delta of t minus ts. One sample is shifted towards the right side delay function, the ts sample time. Here the magnitude is also 1. Another signal, if I am taking here, that signal is a delta of t minus 2ts. Okay, so the signal is shifted from 0 to ts is the first part, and again now it is shifted that signal in the 2 samples ahead. One, it is also varies with respect to the t only up to the infinite. Then now I am taking the another signal, that is delta of t plus ts. Means plus means it's advanced function shifted towards the left side of one sample. It's also a magnitude is a 1. Got it, my dear students? Now another signal I'm taking that as a delta of t plus 2ts. Plus 2ts means the signal delta of t is shifted minus ts is the first sample in the delay advanced function, and towards the left side is a second sample. Now this the magnitude is also 1. So on. Okay, these are ts, 2ts, and all the values also here. Minus ts, minus 2ts. This is 0, and here also 0. Minus 2ts, ts is a value here. There is 0 and 0, and here the ts is there, and 2ts. These two also the 0, and I represent here the 2ts. It's also 0. Minus ts, minus 2ts is 0 here. Minus 2ts 0, and ts is 0, and 2ts is also 0. Now I can add all the signals, the delta of t, delta t minus ts, delta t minus 2ts, delta t plus ts, and delta t plus 2ts. Now add all the signals. Add all the signals means sum of n is equal to minus infinite to infinite delta of t minus the n value n into ts. See, when n is equal to 0, the value will get the t minus 0, that is a delta of t. Delta of t 0. So add all the terms means add the 0, here the 1, it is 0, 0, 0, 0, means 1 plus 0, 0, 0 is the value is a 1. At ts, you can see at ts here the 0, 1, 0, 0, 0. Means again we'll get the 1 more. At 2ts, add all the functions. 2ts here the 0, 0, 1, 0, and 0. So the value is 1. And minus ts, you see here the 0 plus 0 plus 0 plus 1 plus 0. Again we'll get here the 1. I'm adding all the functions. At 2ts, minus 2ts is 0, 0, 0, 0, and here the 1 value, minus 2ts. So all the functions is added. That is becomes of sum of n is equal to minus infinite to infinite delta of t minus n into ts. Where n is varies 0 means we'll get that the 0. When n is equal to 1, it ts. N is equal to 2, 2ts. N is equal to minus 1 means delta t plus ts. Delta t plus ts minus ts. When n is equal to -2, it becomes of delta t plus 2ts and so on. Okay, this is a sampler. Now, combining these two signals, the input signal x of t and this signal, saying that it is a sample delta ts, let us take that. Now, I am combining the two signals or multiplying the two signals x of t into the sum of n is equal to minus infinite to infinite delta ts into t minus n into ts. Taking the delta ts as a sampling version, or without confusion, don't keep here the ts like this, minus infinite to infinite. So the x of t, here the x of t having some value is multiplied with the 1, we'll get the x of t only. For example, minus 2ts and minus ts 0 and 1 is multiplied with the x of t signal. 1 into whatever the multiplication factor, we'll get the same signal only. Ts and 2ts. Okay, varies with the time t and the x of t. That x of t I'm assuming as x delta of t is equal to, you see this is a diagram shown here. You suppose the negative is there, the sampling is also in the negative values only. Means why it is a negative means the x of t is a negative, not the samples here. X of t is a negative means 1 into that negative value, you get the negative term. X delta of t is equal to x of t into sum of n is equal to minus infinite to infinite delta of t minus n into ts. It's also can written as x delta of t is equal to the sum of n is equal to minus infinite to infinite x of t into delta of t minus n into ts. Okay, this is the equation. Now we got this equation is the output of the sampler in the block diagram. The sampler input is an analog signal, nothing but x of t. Inside it is a sampler. Okay, the signal which is band limited to FM head and is completely recovered from its samples. If the samples are rated, that is a statement is a sampling theorem. So first of all, you can take that continuous time signal is converted into the discrete time signal. The output of the sampler. The output of sampler in the mathematical expression x delta of t is equal to sum of n is equal to minus infinite x of t delta t minus n into ts. Delta t minus n into ts. Got it, my students? The signal is a continuous time signal x of t. A unit impulse train is used. It's called as unit impulse train. The sum of n is equal to minus infinite delta t minus n into ts is a unit sample train used as a sampling function. After combining the two functions, x of t and the impulse train, the figure C called it as a sampled version of the signal. Sampled version of the signal in the figure E. Understood, my dear students? How we got this equation? By taking the x of t as a signal and it is sampled with the sampling train, impulse train. And finally, we get the x delta of t is the sum of n is equal to minus infinite x of t, x delta of t minus n into ts. Okay. Here the Ts is equal to the inversely proportional to the frequency. The Ts is 1 by Fs represent the sampling period. We got the delta of t, impulse train. The sum of n is equal to minus infinite delta t minus n into Ts. Okay. And then the signal is multiplied with the x of t. The t is I am taking as a n into Ts. Okay. You see here, multiplying the unit impulse with the instantaneous values of x of t, that is x of n into ts. Following matters, you can write this as x of t, nothing is wrong. X of n into ts is also nothing is wrong. So x delta of t is equal to sum of n is equal to minus infinite to infinite x of t delta t minus n into ts. Thus, x delta of t is represented by the multiplying the equations phi 1 2 is a x delta of t by x n into ts. Since the width of this impulse is in that x delta of t approaches to the zero, it represents only the instantaneous values. Therefore, this method is called instantaneous sampling. It is also called as Idl sampling. Okay, it represents only the instantaneous values. Therefore, the technique what we are using here in the sampling theorem, that is instantaneous sampling. There is a different types of techniques are there in the sampling. The flat type and what are the different types here? They are saying so flat top samples, regular samples, and instantaneous samples, etc. Okay, the different types of samples are also taken. That is a flat top samples, regular samples, and here there is an instantaneous samples, etc. Okay, it represents only the instantaneous values. Therefore, this method is called, whatever we are following now here, the sampling theorem to prove the sampling theorem, is an instantaneous sampling, also called as Idl sampling. And this signal, the time domain signal, x of t or x delta of t is equal to sum of n is equal to minus infinite to infinite delta of t minus n into ts x into x of n into ts is converted into the either x delta of t represents the sampled version of the continuous time signal x of t. The Fourier transform of the impulse train is x of f is equal to fs into sum of n is equal to minus infinite to infinite delta of f minus n into ts. See, this is a time domain signal is converted to apply the Fourier transformation for this to get in the frequency x of f is equal to fs into sum of n is equal to minus infinite to infinite delta of f minus n into fs. So by using the, how we can convert this time domain to the frequency domain function means by using the trigonometric Fourier series. By using the trigonometric Fourier series, see. Okay, we are saying we are applying the Fourier transformation, and by using the trigonometric Fourier series, we are converting the time domain function to the frequency domain function. We'll see in the later.